Hi, good day, everyone. Right, so today we are going to talk about strengthening mechanism. Yeah, as we already know in the previous chapter, when we increase the dislocation density, uh, we know that we also increase the yield strength, which result at a higher shear stress required to move the dislocation. Yeah. So, in terms of hardness and strength, it is very linked to the metal plastic deformation easiness. When we talk about the dislocation movement, uh, it helps to reduce. When we reduce dislocation movement, it will improve the mechanical strength. So we can say that this topic, the current topic, strengthening mechanism that we are going to learn in this video is an extension of previously what we have learned in previous chapter. That is a dislocation, the concept of dislocation in material science. Right, so in this topic, what we are going to learn is a mechanism in strengthening materials. So we focus on metal. So we know that uh, your role as a material engineers is to design alloys with a high strength, ductility, and toughness. But the challenge are to to balance the strength, the toughness, and ductility in alloys. When we increase strength, it often reduce ductility, and we need to find a compromise between this property. So how are strength and ductility related? If you can still recall what we have learned in previous chapter, generally we can say that strength and ductility for most materials have an inverse relationship. As a material scientist, we are often required to design alloys with strength and yet having some ductility and toughness. So we know that ductility is reduced when alloy is strengthened and vice versa. So if I ask you, why do we use steel to fabricate a ship hull? Yeah. So the reason why steel is used because steel is chosen for its high strength. In terms of corrosion resistance, it offers sufficient resistance to rust, and thus it will help to prolong the life span of the ship hull. And in terms of durability, with proper maintenance, it can last for decades. And in terms of cost effectiveness, comparatively, still we can say it is an inexpensive material. And it is quite simple, relatively, to join together, and it is easy to repair if damaged. So, while steel dominates a large commercial ship construction, we still have aluminum, we still have wood, fiberglass, and any number of composites that are used in ship and boat construction. And the Russian, they built a submarine hull out of the titanium, and the selection of hull material is a balance between strength, the corrosion resistant, workability, and cost. So just to recap what we have learned in previous chapter in this location. So we know that the plastic deformation of material depends on the mobility of this location. So if you look here at the table here, what do you think will happen if we reduce the mobility of this location? What are the effects? does it enhance or reduce the mechanical strength? And what happens if we constrain the dislocation motion? Will this make metals softer or weaker, or the opposite? Yeah. So the important concept to know that dislocation motion is crucial for plastic deformation of metal. In terms of mechanical properties, the hardness and strength are tied to how easily a metal deforms plastically. And if we reduce the mobility of a dislocation, what will happen is that it will increase the mechanical strength, and we will require a more force for plastic deformation. So why metals have a much higher density than other materials? Yeah. One of the factors that can contribute to this is a close packing factor. The close packing factor, it will contribute to the high density of metal compared to polymer. Yeah. If we look at the picture here for FCC, it has a 74% packing factor. For BCC, it has a 68 packing factor, and for hexagonal close pack material, packing factor is 74%. And in terms of a metal atomic structure, we can see that the atoms in pure metals are closely packed in a regular grid. And if we compare this with glass, we know that glass has randomly arranged atoms, and glass is amorphous, not crystalline like metal. So strengthening mechanism, we can define it as the ability of metal to deform depends on the ability of dislocation to move. So like what I have mentioned just now, when we restrict dislocation motion, uh, we can make the materials stronger. So when we want to increase the material strength, this can be achieved by inhibiting dislocation motion. And there are many types of strengthening mechanism that we can perform. For example, for single phase material, we can reduce the grain size, and also we can use solid solution strengthening, and also we can apply strength hardening or cold working. And for multi-phase material, we can employ precipitation hardening, and we can utilize dispersion strengthening, and we can implement martensite strengthening. So among the methods that we can do to strengthen material, we can do to strengthen the material is by reducing the grain size. Yeah. So the grain size, it will impact the mechanical properties in the polycrystalline materials. Like what you can see here, we have a grain boundary, as you can see in the figure here. So what does the grain boundary will do? It will hinder, or we can say, avoid dislocation movement by causing directional changes and creating a slip plane discontinuity. As we can see, the grain A and B here, it has a different orientation. So dislocation passing to grain A from grain B will have to change direction. And atomic disorder within this grain boundary will result in discontinuity of a slip plane. So the grain boundary are barriers to slip or dislocation movement. the barrier strength increase with this misorientation. And when we have a smaller grain size, meaning that we have more barriers to slip. And here we have a Hall-Petch equation that I'm going to talk later. So, is fine grain materials harder and stronger than coarse grain materials, and why? Yes, the answer is yes. Fine grain materials are harder and stronger than a coarse grain material. It is because a fine grain materials has a greater total grain boundary area to inhibit dislocation motion. By reducing the grain size, we increase the number of grain and hence we increase the amount of grain boundary area. Any dislocation move only a short distance before encountering a grain boundary, and the strength of the metallic material will be increased, meaning that when we have a smaller grain size, we have more boundaries, and this will lead to a shorter dislocation path and a stronger material. So when we have a grain boundary, it will disrupt a slip plane and can generate a new dislocation. When we have a smaller grain size, meaning that we increase the grain count. So if we have a high angle boundary, dislocation may not cross, but rather it will concentrate it around it to create a new dislocation in neighboring grain. Smaller grain means more grain. Alright, so in the figure here we can see the influence of a grain size. We can see this is the influence of a grain size on the yield strength of 70 copper, 30% zinc, brass alloy. And note that from here we can see the grain diameter increase from right to left. And when the grain diameter increase, we can see that there is a decrease in terms of yield strength. Yeah. So we can say that when a grain size increase, what will happen? What will happen is the yield strength of that particular alloy will also decrease with the increase in the grain size. So now we know that the grains are separated by a grain boundary, and since each grain it has a specific plane along which it's easier for slip to occur. So the presence of grain will inhibit or impedes the motion of dislocation, and so polycrystalline material tend to be stronger than materials that only made up from a single uniform crystal. So the smaller the grain size, the stronger the material will be. And this is captured in the Hall-Petch equation, like what we have here. So this is a Hall-Petch equation where the sigma sub y is the yield strength, and we have a sigma sub naught is a reference stress, and we have a k sub y that is a constant, and we have d that is the average grain diameter, and d is influenced by the rate of solidification, by plastic deformation, inoculation, and also by a heat treatment. So in general, we can say that fine grain is stronger. It is also harder, tougher, and more susceptible to a strain hardening. Right? So why fine grain is stronger? Because adjacent grain have a different orientation, so dislocation have to change direction. Change in direction is harder if large misorientation exists. Smaller grain size also meaning that we have atomic discontinuity where the slip plane will be discontinued. And here we have the model, a pile up model. We have a dislocation pile up model here. As we already know, we know that the adjacent grain differ in terms of orientation. So in this pile-up model here, we can see that dislocation move within a grain until it is stopped or halted by a grain boundary. So we can see here that the grain boundary act as an obstacle due to orientation mismatch between two adjacent grain here. So how do we control the grain size? Right, so we can do this by controlling how fast the metal is cooled. If the metal is cooled very rapidly, we can see that we can observe that nucleation will occur at more location, and the crystal don't have much time to grow, so the metal will end up with a finer grain structure and will be stronger as a result. So impurities that we call as inoculant can intentionally be added to the molten metal so that the crystal nucleation occurs at the more site, leading to a smaller grain size. Another way of we can strengthening material is by performing a solid solution strengthening. Uh, So we can say that a solid solution strengthening is strengthening pure metal through alloying. In this process, we are going to introduce the alternate element atom into the metal lattice, like what we can see in the animation here. And this impurities atom will go either into the substitutional or interstitial. This is what we call a solid solution strengthening. What will happen when we add this impurity atom is that it will create a non-uniform lattice structure, and it will generate a local strain field that will interact with dislocation. Right, so this solid solution strengthening will increase resistance to dislocation motion. For example, we have a brass copper zinc alloy that is stronger than pure copper due to this method. And other than that, we have carbon that we can utilize in steel strengthening. It can form iron carbide that will contribute to the steel strength. And another example that we can think of when we talk about solid solution strengthening is that in jewelry materials, we have a pure gold and silver that are very soft and malleable, and to make the material, the jewelry material a little bit harder, we add a copper to the gold and silver in jewelry to maintain the shape. So in solid solution strengthening, impurity atoms can distort the lattice and generate stress, and stress can produce a barrier to dislocation motion. Right? So there are two types of solid solution. We have interstitial and also we have a substitutional. And both types result in a solid solution that is stronger or has a higher yield stress than the pure element. And as a result, dislocation, it cannot move due to substitutional impurity within the lattice. And why alloys are stronger than pure metal? Because impurity atoms that go into the solid solution will impose a lattice on the surrounding host atom. And within the lattice strain types, we have a tensile strain, where the larger impurity atoms stretch the lattice, and as a result it will create a tension. And also we have compressive strain, where the smaller impurity atoms allow the lattice to compress, and as a result it will create pressure. And like I have mentioned just now, impurity atoms distort the lattice and generate a lattice strain. And as a result, we have a displacement effect with a solid atom. It causes deformation, creating a strain field. And this will cause an interaction. The strain field of a solid atom will interact with dislocation strain field. We will talk more about this later. And also in terms of size differences, when we have a greater size, the differences between a solute and a solvent atom, it will result in more strain. The higher strain will lead to more effective hardening from the solute atom. And interstitial or substitutional impurities, it will cause lattice strain and interact with dislocation strain field, and as a result, it will hinder dislocation motion. In terms of impurity behavior, it will diffuse and segregate around dislocation to match the atomic size, and as a result, it will reduce the strain energy, and also it will anchor dislocation and stop the movement of dislocation. And when we talk about the strain field interaction between dislocation and impurity atom, it will restrict dislocation movement, like I have mentioned about it just now. The solid atom also has its own impact, where the smaller solid atom, it will cause a tensile strain in the lattice, and the larger solid atom will create a compressive strain nearby. Yeah. So when we have a tensile strain and when we have a compressive strain, it will lower the energy of the system, and as a result, it will reduce the mobility of the material. Right, so solid atoms always have a strain field that interact with a dislocation strain field. When we talk about the solid atom behavior, they tend to segregate around a dislocation, and as a result, it will reduce the overall strain energy. And whether the solid atoms attract or repel dislocation, basically we can say that the motion of dislocation itself will be hindered or impeded. So here also not that here we can see this, the higher size differences will lead to the higher strain, and they will be more effective hardening due to solid atom. For example, here we have a base element, copper, with a radius of 1.25 angstrom, and we have 4 different alloying elements. Here we have a strontium with 1.51, beryllium 1.12, and we have a nickel 1.25, and we have a zinc with 1.31 radius angstrom. And here we use substitutional solute of different element with a different radius, and we can see from the figure here, since the nickel and zinc is almost similar radius to copper, the effective straining is a lot less in the plot, and as a result we can see that the yield stress of strontium and beryllium is higher than nickel and zinc because the higher size differences in terms of radius between strontium, beryllium, and copper. So in this table here, we can see the categories of steel based on carbon content and the alloying element. We have a low carbon mild steel, we have a density carbon steel, a high carbon steel, and a cast iron. For low carbon steel, the carbon content is up to 0.25%. In general, low carbon steel, it is not very strong, it is quite ductile and relatively inexpensive. And for medium carbon steel, it has carbon content from 0.25 up to 0.6%, and in general, it is quite stronger compared to low carbon mild steel, and then it can be further strengthened by heat treatments like quenching and also tempering. And also we have cast iron with a good fluidity and a lower melting point due to extra carbon. Cast iron is suitable for casting and it is generally brittle. And adding element to iron carbon mix will help us to tailor for specific property. Yeah. For example, we have a stainless steel. The chromium is added for corrosion resistance. For example, we have a type 304 that consists of 18% chromium and 8% nickel. So the figure here shows illustrate how increasing nickel content in copper will affect its mechanical property. If we look here in terms of tensile strength, the more increased nickel content, we can see that the tensile strength also increase, and the same also happen for yield strength. It rises as the nickel content increase, but for ductility we can see it decrease when we increase the nickel content. Yeah. And remember that yield strength, we have discussed about this term many times previously. Yield strength is marks the transition from elastic to plastic deformation in material.